We were trying to understand the dynamic stability aspects of an aircraft, and we have seen that when we were analyzing longitudinal mode, right, and we could get equations of this form: as4 plus bs cube plus cs square plus ds plus e equal to 0, and you know a, b, c, d, e, all they can be computed using aerodynamic derivatives, inertia properties, etc. And when I solve this numerically, we get solution for a typical aircraft, lambda 1, lambda 2 as minus 1.008 plus minus j 2.651, and similarly minus 0.0069 plus minus j 0.0905. What is important here is to note is that these roots are complex conjugate, right? So it tells you this is oscillatory motion. And whether this oscillation is going to decay or not, who decides that? That is decided by the real part of this root. And if you could see, for both the pair, the real part is negative. That means the oscillation will damp out. We all know for a second order system, right? Now, there is another difference that you could see this value is minus 1 and this is 0.0069. So which one will decay faster? This will decay faster. So this excitation, almost like a second order excitation, this will decay faster because you know that for a second order system, if decay is like this envelope is governed by e to the power real part into t, okay? And real part being negative, so naturally this will decay faster as compared to this, right? So what we have seen for mostly for a business type aircraft, you'll find the solution of this equation will result in two pair of complex conjugate, this one lambda 1, lambda 2, and lambda 3, lambda 4, and in one pair the real part will be largely negative, larger than the other roots, real part. And physically what we understand is, when an aircraft is disturbed, it has primarily two modes of excitation. One is short period, that you disturb it and immediately comes back. And during this short period mode, you can understand there is no much change in the velocity u. Okay. However, this is a long period because it takes longer time, and it is something called a Phugoid mode. It oscillates like this and then comes to the equilibrium. So we will now do a short period approximation with the understanding of this sort of a background, and we will do this short period approximation. And let me write the equation first. So you could see that this is our standard equation: s minus xu minus x alpha, then g, and then minus zu, then s into u1 minus z alpha dot minus z alpha, then minus zq plus u1 into s, and minus mu minus m alpha dot s plus m alpha, then s square minus mqs. This, of course, into u of s, alpha of s, theta of s equal to x delta e, z delta e, and m delta e. To be more precise, we write it like this. Theta is like delta e. You should note down that we are not writing q here because we have understanding that q is equal to theta dot for small perturbation. So q of s is nothing but s theta of s that was substituted there. So that is fine, that is part of algebra. Now we are almost going towards applying short period approximation. And what is the short period approximation? That during this disturbance or during this excitation, the u remain constant. There is no change in the u perturbation, right? Or u perturbation u is 0. Because you can understand this is very short period. In very short time it comes back to equilibrium. So that's not a bad approximation. So why to handle all those 3 by 3 matrix? Since u anyway is not a matter of concern for us, so what we do, we neglect this term. This 1, and here we neglect it, and then we get an equation of the form determinant is S u1 minus z alpha dot minus z alpha minus zq plus u1 s minus m alpha dot s plus m alpha and s square minus m2s. Okay, so this stability matrix now get reduced to this, and I am directly writing the determinant because I want to find the characteristic equation, and I know the determinant equal to 0 will be the characteristic equation, right? So if I write that, then I get an equation which will be very, you will see that very handy for a designer to design an airplane. Before I go to that, please note down here, this is G, means I have taken theta 1 equal to 0, which is fine. I'm going like this at steady state. And also when I do it here, if I assume z alpha dot equal to zq and also theta 1, all are identical to 0. And please understand here, we have not incorporated the thrust term, right? So no thrust term is included because we know that if we understand this, how to derive this, adding thrust term is no way different than handling the drag term. Okay? So this no thrust term is included, please note down this. So when I write the determinant equal to 0, I get an equation. Now we are looking for characteristic equation. So characteristic equation, and that will be determinant of this equal to 0, and that will give me a result something like this. Determinant is S u1 s square minus mq plus z alpha by u1 plus m alpha dot s plus z alpha m2 by u1 minus m alpha, right? And that will be equal to, so this S1 will be somewhere here, this is equal to 0, right? Now this equal to 0 means that this one is 0 or this one is 0 or both are 0. So from this you get S equal to 0, 1. Solution another is this whole term equal to 0. X equal to 0 is obvious. This is some sort of a neutral stability because airplane, whether it goes straight, goes like this or goes like that, this as far as aerodynamics is concerned, it is same thing for it, right? So we will not take this solution at all, and we'll use this equation, and then we get the final characteristic equation for a short period as S square mq plus z alpha by u1 plus m alpha dot into s plus z alpha m2 by u1 minus m alpha equal to 0. As simple as that. Okay. But you see that when I do a short period approximation, we have got equation which is second order equation, and we are very much handy in handling this equation because we know if I want to find out damping ratio and natural frequency, I have to only compare it with this form which we have already derived. So now if I compare, what do I get? If I compare, I get omega n short period equal to under root z alpha mq by u1 minus m alpha and zeta short period equal to minus mq plus z alpha by u1 plus m alpha dot by 2 omega n short period. So this is basically we are getting for short period. Let me repeat again. When the airplane is flying, if there is a excitation from the external disturbances, the airplane will have a tendency to get excited primarily in a short period or a Phugoid mode. What is short period mode? Disturbance, and it comes back like this. Another is, it comes back to equilibrium through a conversion of potential and kinetic energy, but it's a long period. But we're talking about short period, which is this. What is the assumption in short period mode? And how we have simplified the equation? We have assumed that the short period mode means u will not going to change. So the 3 by 3 matrix we have converted into 2 by 2 matrix by neglecting u equations, right? And we have got the natural frequency for short period and the damping ratio for short period mode. Okay. This is a very important relationship, short period mode. You see in the design or the designing of SAS, stability augmentation system, we often use this as our initial relationship for developing the final solution. Okay. Now we come back to the Phugoid approximation. As far as Phugoid approximation is concerned, it is not really very good approximation, and but however it gives some good result. And the Phugoid approximation, what is assumed is the alpha degree of freedom to be superfluous. What is the meaning of superfluous? That we are telling that during Phugoid mode, the approximation, which is not very correct approximation, but it is not that bad also. It's not a worst approximation. It's not a very good approximation, but it gives you some feel. So in the Phugoid, it's assumed that the angle of attack perturbation that remains same. The angular attack remains same. So angular perturbation or in terms of angle of attack is neglected. Okay. In a short period, it was u that was neglected, right? So with that, so alpha remaining constant is the approximation. And if you do that, then you will get an equation. For you, it is important to just note down this. Right? You could easily find out which one has been omitted. U of s by delta U of s and theta of s by delta U of s. You could see no alpha is here, so it is 2 by 2 matrix is equal to x delta E, z delta E. And now the characteristic equation becomes very simplified. And let us see for Phugoid what are the additional things we are going to get. Please remember this part of dynamic stability needs to be treated as a different course altogether. We may come up with a 10 hours course on dynamic stability because it's huge. But we are giving you some flavor so that you are ready for next course. So don't get disturbed because of so many equations, so many interpretations are coming. Try to make an attempt to understand it and make yourself ready. If I do this, then I find from this that U of s by delta E of s is z delta E into g by u1 s squared minus xus minus zu by u1 g, and theta of s by delta E of s is z delta E into s minus xu by u1 s squared minus xus ZU by U1 into G. So what is U of S by delta U of S? This is called the transfer function. So from the short period also you know that alpha of S and delta U of S are transfer function. So these are called transfer function. Okay. Now if I want to find the roots, then what I have to do? I have to ensure that this gentleman is 0, this is the characteristic equation. So if I put that to 0, what happens? If I put that to 0, I get x squared minus xu s minus zu by u1 into g equal to 0. So again you see, this is of the form s squared plus 2 zeta omega ns plus omega n square equal to 0. So I know omega n is equal to under root of minus zu by u1 into g and 2 zeta omega n equal to minus xu, that's all. Okay, or zeta Phugoid, okay, is equal to minus xu by 2 omega n Phugoid. So I call this Phugoid. You know by now what is ZU, what is XU, right? All those expressions you are aware. Now we'll do a little bit of work on this and you'll see that what happens. Let us see omega n p. Take omega n Phugoid and try to extract meaning out of it. See that omega n p Phugoid is under root of minus ZU by U1 into G, right? And for ZU, you know the expression, so I'll put that, this is equal to G by U1 is already there, and this is Q1 S into CL alpha plus 2CL1 by M U1, okay, which I can approximate it to under root of rho GS by M into CL1. What has been done? That is, if you see here, this is CLU. This is not CL alpha, sorry, CL, corrected. This is CLU, okay? What is the approximation here? That I have neglected CLU. That's CLU, which is nothing but M1 into dCl by dm. I have put it to 0. That is, typically I am talking about a subsonic airplane up to Mach 0.6. What is Q1? Q1 is half rho U1 square. So use, for Q1 you use this. The moment I use this, you should be smart enough to get this expression. Okay? This is the expression. How do I get from here to here? You are smart now. You know Q1 is half rho U1 square. So put half rho U1 square here. In the U1 square will get cancelled. Then 2CL1, the 2 will get cancelled and you will get rho GS by M CL1 under root. So omega n Phugoid is under root rho GS by M CL1. And what is CL1? CL1 is nothing but W by or mg, W means mg by half rho U1 square. If I put in this expression, I get omega n Phugoid as G root 2 by U1. Could you see this? For CL1, so here under root of rho GS by M and CL1 is mg by half rho U1 square. So you could see that half goes here, rho get cancelled, G remains, M will get cancelled, so get this expression. Right? So what is the message here? For a Phugoid mode, you see its natural frequency in Phugoid mode is inversely proportional to the forward velocity U1. So more U1, this frequency is less. Okay? Right? Very, very, very important observation. And further you could see for zeta Phugoid, let us see what does it mean to us. See the expression zeta Phugoid we got as minus xu by 2 omega n phugoid. And this, if I put the expression of xu, I get q1s cdu plus 2 cd1 by 2 m u1 omega n phugoid. What has been done? We have substituted the expression for xu. And what was xu? If you see, what is the expression of xu? xu is minus q1s cdu plus 2 cd1 divided by mu1. Nothing big thing we have done. q1s cdu by 2 mu1 and divided by omega n here, omega n here. Right? Although it looks something big, but as simple, as straightforward. Now we know omega n phugoid is g by u1 root 2. Please understand here, from the beginning we are analyzing this assuming no thrust effect, right? So it's like a power off case. And I have been always telling the thrust and drag of similar nature. So you can, whatever you do it here, you can expand it for thrust also, right? So now when omega np is this, if I substitute here and also I write mg, please do yourself q1s cl1, right? Or m is equal to q1s cl1 by g. If I substitute this, omega np here, and for m I substitute this expression, then I get zeta p, very important relation, as cdu plus 2 cd1 by 2 cl1 root 2. Okay? And if cdu is 0, that means you remember CD versus Mach number up to 0.6 or 0.7 is very constant, then goes like this, and CDU is nothing but M1 dCdu by dm. So up to this point, this dCdu by dm is 0. So for a subsonic case, I can neglect this. So zeta p CD1 by CL1 1 by root 2. Okay, see this goes. This cancels, so this is the expression. What is so important about this expression? Why I am using this so not so good approximation, but still I am telling, let us do that. CL1 by CD1 root 2. It tells you that if CL by CD is large, which is essentially true for gliders and all, or in general you try to get CL CD large, but you should be careful by doing that. Your damping ratio for your Phugoid mode will become weaker and weaker. That is very important, right? Okay? So slight excitation, it will take a lot of time to damp out the Phugoid mode. So this is very, very important. Okay? So we have finished it here. Now, the longitudinal part is concerned. What we'll be doing, we may immediately go for stability augmentation system, how to design in one lecture, and then we'll give in one lecture the lateral directional case, which will not complete in exhaustive manner because enough. I'm sure by now you may be feeling tired, and then we'll wind it up and we'll please try to derive this relationship. Okay? Thank you.